Hello all, welcome to this tutorial wherein which we will be learning about the implementation of variational autoencoders, VAEs. Let's do a very small recap on the aspects of VAEs. So we are looking at variational autoencoders, VAEs, now, which is a latent model. So we want a latent variable model. So you have been given data D now, which is xi I is equal to 1 to n, now which is sampled IID from distribution Px, and xi belongs to Rd. So now what is the latent variable model condition that has to be satisfied? Now, which is p theta of x is equal to, if you integrate over the latent space over the joint, okay, now you should be getting p theta of x, in which the z is from Rk, and typically during implementation we see to it that this k is quite less than d. So and then we want such a theta star such that we have argmin of the KL divergence between the data distribution Px and then the distribution P theta, and we know that this can be written as, I'm just skipping algebra here. Now I assume that these steps are pretty much known to you. This is expectation with respect to the data distribution Px over log of P theta of x. And then from here, I assume that you know how to derive the elbow. I'm just keeping it as dots. This is nothing but argmax of theta. We call it as j theta q. Now, just for remembrance, now this is argmax of theta. Now you have expectation over the variational latent posterior. Now that is q phi of z given x log of p theta of x given z minus the KL divergence now between the latent posterior, that is q phi of z given x, and then the latent prior, now which is p theta of z. Okay, now this is your function which we need to optimize. Now here, if you recall, p theta of x given z is what is called as the conditional data likelihood. Is called as conditional data likelihood, and then you have q phi of z given x, now which is variational latent posterior. Okay, latent posterior, and both of these distributions which are there, now we want to represent them using a neural network. Okay, now this is what we want to proceed. Now here your encoder model will give you the parameters of the distribution. So we know that procedure Y, we chose that there were two things. Now in which we chose one, now in which it will give you the parameters. Okay, so now coming to the structure of how do we do it. Now you have an encoder model which will take x, and then it will give you the parameters, and then you have a decoder model is this. That will take Z and then give the parameters of the data generations. So now you take X here, X, and then you will get the parameters Q, the mean of it, okay, and then you get the variance. Now this we are assuming a diagonal variance, so therefore what will happen is now you get mu1 to k, okay. Now, since we are assuming the diagonal, now we will be only getting the diagonal element, not the whole matrix, okay. So now this is q phi of z given x, okay. Now x is the input, you get these things. Now once you have obtained that, this is encoder. Now this is the encoder model, okay. Now then we perform the because of reparameterization, so we know that zi that we want to do, what we want is q phi of xi Hadamard product with a sample from standard distribution, okay. Now here xi is in RD, your zi, and then the mean, now both of them are in RK, okay, and then your xi, now this is in RK cross K, but you're only getting the diagonal elements as an output from the encoder, okay. So now to the decoder, which is represented by another neural network, which is p theta of x given z. Now this will take this zi as an input, and then it will give x kappa phi. Okay. Now this is the overall structure. So now how do we perform? Okay, this theta of z. Okay. This is how we can represent it, so that we know that it is generated. Now this is the overall structure. So now let's remember now how does it performs the forward pass. Okay, let's recall the forward pass. The forward pass here. Now step 1 that we do is, now given xi from D, we pass it through the encoder and then we obtain the mean and sigma, mu and sigma. Okay. Now we have xi belongs to D. Now you pass it through encoder. Now this is this is the forward pass. Okay. Encoder, and then you get mu phi of xi and the, okay, so you obtain this, and then the second step is, now you sample epsilon 1 till epsilon m from normal distribution 0i. Now this is outside of neural network. Okay, this is outside of neural network. Now which should be evident from here. You obtain these, okay, and then you sample epsilons, and then you finally obtain zi. Okay, this is outside of the neural network. So then what you will do in step 3, so you compute z1 till zm. This is done via reparameterization. This is done via reparameterization. Then the fourth step, you pass these Z1 till Zm via decoder, and compute x cap theta of Zj. Okay. Now this is what you do. This is your forward pass. Now the question is, how do you perform the backward propagation is the question. So now to perform backward propagation, see, you have two sets of parameters. Now you have theta and as well as phi, and you have two terms here. Now for the first term, also you should find gradient with respect to theta and gradient with respect to phi. And even for the second term, now we should find gradient with respect to theta and gradient with respect to phi. Now because of which, now you need to compute four terms. Okay, so now let's try to do it. Now first let's look into how do you train the encoder. Now to train the encoder, okay, now the encoder, if you look at the encoder, now encoder is parameterized by phi. So now you need to take the gradient of this term with respect to phi, and then the gradient of this term with respect to phi. Okay, that is what you should be doing to train the encoder. And then to train the decoder, so which is represented by parameters theta. Now you should be obtaining the gradients of this first term with respect to theta, and then the gradient of the second term with respect to theta. Okay, so now let's try to do that. Okay. So now obtaining gradients, gradient with respect to phi and theta. Okay, let's do that. Now let's take training the encoder. Let's take the part of training the encoder part. Now in training the encoder, now let's take the first term. So term 1, now training the encoder, that is with respect to, so we want the gradient with respect to phi. Okay, the term 1, now what do we want? The term 1 that we want is, we want the gradient with respect to phi, expectation of variational latent posterior q phi of z given x into log of p theta of x given z, and then we know that via reparameterization now it will become, so the expectation with respect to p epsilon log of p theta of x given g of epsilon. Okay, now this can be looked into expectations. You can write it as some more samples. So j equals 1 to m log of p theta of x given g of epsilon j. Okay. So now, now we know that p theta of, let me change this color, this is similar, so I want to, so now we know that p theta of x given z that we have is from the distribution normal x cap theta of z comma I. Now we are fixing this distribution, because of which what will happen, your log of p theta of x given z equals log of 1 over 2 pi to the power of d by 2 exp of x minus theta of z, the second norm of it. Now if you take the log inside, now this will be proportional to, okay, this is not alpha, this is proportional to x minus of Z, the second norm. Okay. So now if you substitute this in the equation that is here, if you substitute, you take this and then you substitute it here, now then your the gradient term that you have will be proportional to, again, I'm just hitting it. So now this will be minus 1 over m summation j equals 1 to m xi minus a second now. Okay, now this is the term. No, this is nothing but the reconstruction. Now this is the MSE between two matrices. Okay, so now there is a very nice knack here. I leave it as a small teaser. Now, if your image is having values between 0 and 1, now then this can be looked as the BCE, binary cross entropy. Think of it how. Okay, so now with this, now to obtain this, what we will do? Now to obtain this, we keep the parameters of the decoder, which is theta, as constant. Okay. Now, what did we do just now? We just obtained how to look at the gradient of the first term, now, which is in our function, objective function. We just took this term and then we took the gradient with respect to phi. That's all we have done till now. So now let's take the second term. So let's take term 2, which is dKL of Q phi of C given X and P theta of Z. The term 2 that we have is the KL divergence between two distributions. So now, if you remember, now this we are restricting to be a Gaussian, okay, and then there is a standard derivation for this. I urge you to look at that specific derivation, because of which what will happen is this whole KL divergence. Now, if you have this as a fixed distribution, now what will happen is it will turn out to be a straightforward equation. I'll just write that equation down, that is minus half log of the x that is there minus k, which is the dimension of the latent space, and the trace of the matrix plus the norm of the mean. Now this is the value. Okay. Now this is, and as you can see here, now this doesn't have theta at all. This term 2 which is there, okay, now irrespective of the gradient with the respect to phi that you're taking, now this term 2 that is there is independent of theta. Now because of which the term 4 that we want to find the gradient of the gradient to this term with respect to theta, you don't need to look at it at all, no, because it is independent. Okay, so now only this is needed for calculation of the gradients of the encoder. Okay, so now this we represent it as L. Okay, now this term what we will do is, now typically we will add this term while updating the parameters of the encoder. Okay, so now this term will be added when when updating the parameters of the encoder. Updating the parameters of encoder. Therefore, your gradient update will be like phi of t plus 1. Now what you will do, I will do phi of t plus some learning rate alpha and the gradient with respect to the elbow. Okay, now how do you get that? Now you calculate this term, you add them, that will be your gradient. Okay, and this is the standard update. This is how you train your encoder. Now to train your decoder, so to train your decoder, that is you want to take the gradient with respect to theta, so j theta of phi, this will be the gradient with respect to expectation of the variational latent posterior log of p theta of x given z plus the theta with respect to this DKL term. As it turns out, as I told you, this is independent of theta. So you don't need to worry about it. So now you need to calculate this specific term, and we know how to do it. Okay, as it turns out that now it is the same term. Now you have to take the gradient with respect to the theta here. Okay, and then you just stop at the decoder. Now you will not take the reverse path. Even the encoder, you will stop at the decoder. This is how you just do it. Okay. So now the idea is the reverse path, that is the backward path. The backward path stops post decoder. You will not go to the encoder. Now how do you have it? Now your theta t plus 1, theta t plus alpha times of j theta of u phi. Now this is your gradient update. Okay. So now I urge you to look at the posterior collapse. Okay. Now since you are forcing in your decayed term, this is your decayed term, you are forcing your variational latent posterior to one distribution. Okay, for all x you are forcing it. Now because of which if you have two samples, now there will be not much difference now between them. You cannot differentiate between the samples. Now because of which there is the problem of posterior collapse. Now if you sample enough examples from the distribution, you will be able to see it. Okay, so this is the idea of how do you work with this is the theoretical idea. So now let's look into the implementation of it. Implementation is a pretty straightforward one. These are the necessary libraries. Now I will not be explaining about the necessary libraries that are there. Okay, and then this is you're transforming your data. I'm doing a very minimal transformation. Now I'm just transforming it into the tensor. Okay, I'm not going further than that. Okay, so now then you have your beta. See, okay, whether VAE and beta VAE, always we implement beta VAE. Now, if you put the beta value to be 1, which is same as the vanilla VAE. Okay, so now that should be clear. Now, I'm using a convolutional network in this case. Now, whatever is the latent dimension, that is the dimension of Z is given. I'm putting it as default as 20. Yeah, you can enhance more depending on the data structure. So if your data is MNIST, now this is enough. If you are looking into much more difficult data, at that time you should have latent dimension to be even more. Okay. So and then you have your encoder. Now, I presume that by now you should be comfortable with looking at the structure of CNNs, and then you flatten it up. Okay. Now then you have a linear layer to get the mu and then the sigma. Okay. Now you have the from this. So this is 128, 4 cross 4. You are flattened it up to the latent dimension 20. And even your sigma is 20. And then you know that why we are putting even sigma to be 20? No, because we are only getting the diagonal elements. Okay. So now that is what you are doing. And then this is your decoder. It will take latent dimension to 128 4 to 4, 4 cross 4 into 4. Okay. And then from there, now then what do? You obtain it into the size of the image. Okay. So you get it 132 32. Okay. And what do you do 132 32? You finally get only 28 28. Okay. Because that is the standard size of the MNIST, right? Now, post this decoder, which is the transposed convolution that we have. Okay. Now, then what will happen is, now you get it to 1, 32, 32, and then from there you only take 28, 28. You only take 28 columns. Okay. Now, this is the encoder. Okay. Now, encoder will give you the parameters mu and sigma. Now, you will pass an example through the encoder. Now, you will get this block. Now, this is the encoder, nn.sequential encoder block. And then you flatten it up. Okay. Now, then you obtain mu and sigma, and then you send it out. And this is the reparameterization that happens. Now, mu plus sigma into mu plus EPS. Now, this is your epsilon. Okay. Into the standard deviation. This is what you do. Okay. And then you decode it. Now you get this Z, which is obtained from the reparameterization. And then you convert it into 12844. And then you pass it through the decoder. And then you obtain only, you get only the 28. Now, because as I told you, the output will be 32 cross 32. Now you only get 28 cross 28. Now this is the encode process, reparameterization, and then the decode. You combine all of them in the forward method. Now you give the X, you pass it self.encode. You call this encoder method, which will give you mu and sigma. And then you pass that mu and sigma into the reparameterization. So you obtain Z. You pass that Z into the decoder. Now you get your X hat. Okay. And then you pass your X hat, mu and sigma, all of them out. Now, why are you passing all of them out? No, because you want to calculate the loss. Okay. Now, if you remember to calculate the second term of the encoder, you need mu and sigma. Now, because of which you are sending it out even with the reconstruction. Now, this is your calculation of your beta VAE loss. Now, as I told you, the reconstruction loss, now when you are having a sigmoid at the end, okay, now your MSC loss now will be same as the BC loss in that case. Okay, now this is your reconstruction loss which is there. Now that is that second norm of X and the generated X hat, and this is your KL. Okay, now this you'll be able to look at. So now then what is your overall loss? Now reconstruction loss with beta times KL. Now this is that beta value you are putting it there. And then you are sending reconstruction loss and KL loss so that you can put it in the list and then finally see how they are reducing. Okay. Yeah. And this is you are using the device and then you're creating a model and you're obtaining the parameters of it. So you're training it for 10 epochs and then you're keeping beta as 4. Now I urge you to enhance the beta. Now from now take different betas from 1 to 25, take it at 2 steps, and then even less than 1, from 0 to 1 also you take it, and then see how FID score changes. Now you have access to the FID scores as well. Okay, yeah. So now let's look at the training procedure. Now for number of epochs, you just want to iterate. You take a batch, you take X and then port it onto the device. You send through the model. Now model is nothing but having all the three blocks. Now, that is your encoder, reparameterization, and then decoder. Now you pass it through, you get your X hat as well as mu and sigma. You pass them, and then because of which you get the loss, the reconstruction loss and KL loss from this specific function. Now, this will give you all of them, and then you obtain you zero grad all of them. Then you obtain the gradients. Then you go ahead and perform the optimizer dot step, which will update the weights. And then you're just bookkeeping of all those things. I have run this code already, and then I'm just showing you the outcome of this. Okay, now otherwise the time, it will take much time into running. Okay, and this is the loss plot that I have shown here, the K loss. So now one thing I urge is that since you have enough list to plot all three of them separate. No, you will not be able to see nice variations if you put all of them, because of the scale. If you put all of them into one graph, it will not be good. Now how do you generate an image? Now you want to generate an image, you sample from random. Okay, you take the Z. Okay, now you know that. Okay, now how do you perform the sampling now? Okay, I'll just reiterate over the sampling. So now if your training has happened properly, now your KL term will ensure that your Q phi of, that is your latent posterior, has been similar to standard 01 for all X. So now what does this mean? Now if you are sampling from 01, now it is same as sampling from your latent posterior. Okay. So now what do you do? Now the output of the decoder is this specific value. Okay. Now you pass this Z new, which is there, through the decoder and obtain this. Okay. Either you use this itself as the newly generated example, or what do? You sample from the distribution and obtain more points. Okay. Now in this current implementation, what we have done is we are using this itself as the example, and then we'll be doing it. So now you sample from 01. Now how many images you want and what is the latent dimension. Now this is your batch size and this is your latent dimension, which we have fixed as 20. And then you will pass it through the decoder, and then whatever comes, you are porting on to the CPU. These are the generated images that you have obtained for beta VAE, where in which beta is 4. So now, if you see here, now we have just discussed this whole theory. I just want to bring it to your notice that if you put beta here, okay, this becomes beta VAE. If beta equals to 1, this is standard VAE. Now we have looked at the implementation of beta VAE. Now you can put 1, then you can go ahead. And then you can see that now these reconstructions are not so great, because I have trained it for a very small number of epochs. Now you can try it out for more number of epochs and then see how your reconstructions actually are better. So you can try it over different values of beta and then see how you get better reconstructions. Okay. With this, we will conclude the tutorials on beta VAEs. Now we will meet in the next tutorial and look at the VQ VAE. Okay. Thank you.